All right, everybody. Welcome to another episode of Robo Papers. Super happy to have Seohong Park joining us today. He is one of the authors of this paper, Horizon Reduction Makes RL Scalable. And I think, in fact, more importantly, besides the paper, he actually wrote a really good post. I think it's a phenomenal read. I encourage everyone listening to go and read that too. It's called Q Learning is Not Yet Scalable. I actually read this like twice or three times. So I think fantastic job on writing that. I was super looking forward to this episode. Took some time to arrange this, but I'm glad finally we got on the call.
For having me. My name is Seohong, and I'm currently a PhD student at Berkeley working with Sergey. And my main research interests are around reinforcement learning, RL, and in particular, data-driven RL, including offline RL, offline to online RL, and those kind of things, and RL pre-training, such as unsupervised RL, and finally, RL scaling. And today, I think I'm going to talk about RL scaling mainly. And in fact, I think I'm more like an RL researcher rather than a roboticist. But I do think robotics is one of the most important applications of RL, so I'm also fairly interested in it. Yeah, that's like a little bit about myself, and nice to meet you guys. Cool. So yeah, this is the thing that I'm gonna talk about today. So the title is RL scalable? So, I mean, we know scalability is really important. Like, for example, we have scaled off next token prediction to get ChatGPT in language model training. And we also scaled up like diffusion models, flow matching to get like awesome image and video generation models. And we are also somehow scaling up things in robotics as well. So we can also ask whether RL is also scalable, or maybe there are some caveats in it. So that's like what I'm going to talk about today. Well, apparently, it is. Like, for example, 9 years ago, there was like AlphaGo. At that time, I think it beat one of the best player in the world by scaling up RL with a lot of parallel compute. And maybe 2 years later, there was like OpenAI 5 for a mobile game called Dota 2. And there, I think at that time, this agent can also could beat one of the pro players at that time. And recently, people are really excited about like LLM-RL, especially in the context of reasoning. So there's like ChatGPT o3 and DeepSeek R1 and like Grok 4 and all the like RL, LLM for reasoning stuff. So apparently, RL seems to scale pretty well, and we have been scaling up RL, and we are still like doing that, which is good. But if you carefully think about this, there's actually one caveat behind the successes of RL, especially like these three instances. So the caveat here is that all of these successes of RL are somehow trained with on-pulse RL. Like, for example, AlphaGo is trained with MCTS, Monte Carlo tree search, and its follow-up works like mu0, they are also based on Monte Carlo returns in some learned models. And OpenAI 5 is trained with PPO, which is also pulse RL algorithm. And DeepSeek is also trained with GRPO, and all the reasoning stuff are mainly trained with on-pulse RL, like PPO, GRPO, and reinforce, and so on. So that's like one interesting kind of common ground among these like three successes. So just for recap, in RL, there are like two main paradigms. One is on-pulse RL, the other one is off-pulse RL. So this is a kind of recap. So in on-pulse RL, we kind of start from a policy, and then we collect some tuples, like data sets from the current policy. And then when we train the policy, we can only use the most recent samples, just sample from the current policy. And then after performing one gradient update or a few gradient update, we must discard the data. So in other words, we can only use the most fresh data, and that's maybe why it's called on-pulse RL, in the sense that we can only use like on-the-fly data from the current policy. And these methods include like policy gradients, including reinforce, A to C, PPO, GRPO, and so on. On the other hand, so here, my mental picture is that off-pulse RL start from a data set. It can actually be an empty replay buffer. And then this data set actually can be just anything. It can consist of some previous examples or some human demonstrations or even random transitions. But an off-pulse RL should be able to use any data set to train a good policy. And then we can, if you want to close the loop, we can also add back some data collected by the current policy to the data set. So it's in some sense a bit more flexible. And the algorithms are usually Q-learning, so including like DQN, SAG, TD3, IQL, etc. But there's like two distinctions, two categories in RL. And what I was claiming in the previous slide is that most of the real-world successes of RL are based on pulse RL. And as you can see here, on-pulse RL is a bit more restrictive, right? Because you can only use the fresh samples. So you can also imagine that it's a bit more sample inefficient. So that's like one downside of on-pulse RL. So anyway, based on the success of RL in LLM land, we can also think about bringing that kind of recipe to robotics, right? Can we, for example, do GRPO in the real world for training some like really intelligent robots? That's like what we can kind of think about. But actually, if you think about it, this is actually almost like a disaster. So for this, I actually took a tweet from one of my lab mates, Kyle, and
Of course,
I
Kyle.
think, yeah, he did some napkin
Kyle.
math to compute like how many a lot how many like how much time we need to replicate the GRPO's like DeepSeek Auron's GRPO recipe. So what he found is that like 100 GRPO steps correspond to like 1 to 2 weeks of robot time. And as far as I know, the original DeepSeek Auron agent is trained with like 8,000 GRPO steps. So that kind of corresponds to 2 to 3 years of like real robot time for training a single model. And actually, it's also one of the model size. So no matter how large or small your model is, in order to like run GRPO for like 8K steps, we really need like 2 to 3 years of like robot time, where a human must be present next to the robot like 24/7 to reset things and then to clean up things and so on. It's like kind
and
of
it's not just resetting. It's what if like after the first step it kills itself.
yeah, exactly.
You need to buy a new robot. That is the restart.
So it's not just about like GPU time, it's also about like CPU time and maybe robot code. It's like almost infeasible. So I think in my mental picture, so this is kind of what I think about like sequential decision-making problems. So maybe this is the set of entire sequential decision-making problems. And in my head, I feel only a very few tasks can be solvable with on-pulse RL. And somehow, coincidentally, they include games and LLMs. And maybe that's why we are kind of seeing like successes of RL mainly on these domains. Like in games, we know the rules. Like for chess, we exactly know like how the board game state should be changed, and then we can actually just execute them pretty easily. So we can actually collect a lot of unpulsed samples. And LLMs, it's even easier, right? There, the dynamics are just like concatenation, so there's nothing we need to compute. But if you think about this, in many other problems like healthcare, finance, industrial control, and maybe importantly robotics, it's really difficult or almost infeasible to collect on-pulse rollouts. Like for example, for healthcare, probably you don't want to do on-pulse RL with my health or something like that. So for these problems, we really need some like scalable off-pulse RL algorithm to actually apply RL to a real-world problem, especially including robotics. So, this is the question that I initially asked. Is RL scalable? But actually, I want to modify this question, especially in the context of robotics. In robotics, maybe a more relevant and more important question that we should ask is actually, is off-pulse RL scalable? And in particular, if you think about Q-learning as one of the representative methods in off-pulse RL, we can ask whether Q-learning is scalable. So yeah, that's like the main question that I'm gonna try to answer today.
Okay, so before we move on, one question though. So we all know, right?
Yeah.
I assume that everybody who watches this would know too, that like on-pulse RL is the standard way that we do certain things for robotics, like locomotion or like balancing. Could you comment on this? Like what makes it reasonable for that, but not for other tasks?
So basically, maybe you mean training some pulse in sim with on-pulse RL?
Exactly. So basically sim is the answer.
That's actually a very good point. So basically, if we have simulator, then I think we are more like in this situation where we have kind of a model. So we can actually do on-pulse RL. We can somehow scale it up by using parallel, like massively parallel simulation. That's like possible for indeed like for some locomotion tasks like humanoid control or some tasks where we have sim. But I think, and actually this is kind of pretty long-standing debate whether the way to go is like sim to real RL or more like real world RL. And probably I'm not sure whether I can provide a very satisfying answer to this like controversial question. But I think what's clear to me is that at least for some tasks, like especially manipulation, where we want to perform some like free-form object manipulation kind of things, it might be really difficult to actually build a sim and then do on-pulse RL in it. Maybe it might be even cheaper to actually hire humans to do like 2 to 3 years of robot like rollouts than actually building a very physically realistic sim that abides by all the like natural physics. Like maybe that requires like some PhD like some employees. as opposed to some like human demonstration, like data collection or something like that.
Good. Okay. So these are like your t-shirt folding kind of domains, like all these manipulation tasks that just we can't really simulate well. So
That's
there's
true.
tons of very good places for off policy. All right, cool.
So in that case, we want to use some previously collected data, or at least we want to reuse some data to minimize the human effort. Okay, so that's the question. But I mean, this is actually still slightly vague. Like, what does it mean by scalable? So let me pose a more concrete question. So this is the more concrete question that I'm trying to answer today. Basically, yeah, with an infinite amount of data, compute and model capacity, will existing Q-learning recipes solve any task? So I'm asking whether it's a data problem or it's an algorithms problem. So if the answer to this question is yes, then actually what we have to do, what we should do right now is that instead of like developing a new Q-learning algorithms or something like that, maybe we should actually think about ways to collect better data, or actually scaling up compute, or like developing some systems that enable like scaling of RL or something like that. If the answer is no, then maybe what we should do right now is like more like algorithms research rather than actually trying to scaling up current algorithm. Because if there's no guarantee that existing Q-learning algorithms can like solve any task with like a lot of data, then maybe it might the effort scaling up might be potentially like futile. So it's kind of, like in computer vision, like around 2015, we have like GANs, generative adversarial networks. And we kind of know that relatively, GANs are less scalable than diffusion models. So I'm asking whether we are in the GAN area in this off-pulse RL, or maybe in diffusion era in this off-pulse RL. So that's like the question that I'm trying to answer. And this is the main theme of this paper called Horizon Reduction Makes RL Scalable. Yeah. So in this paper, we actually try to answer this question by actually doing this in some sense. So what we did here is that we first prepared some previously unsolved, really complex robotic tasks. So here, for example, in the middle task, so this is a puzzle task. And by the way, here, the action space is actually the robot arms like XYZ displacement or something like that. It's not like semantic actions, but it's actually, manipulation task. So we need to like control the robot to actually press the button. And whenever the robot presses a button, then the colors of that button and the adjacent 4 buttons get flipped. And the goal is to reach some goal configuration. So in this particular case, the robot is supposed to turn everything in red. And then to do that, you need to carefully press like some combination of the buttons. It's really hard, even for me. And this is like cube manipulation, where we have like 8 cubes. So the robot has to perform 8 consecutive pick and place manipulations. And also it's goal conditioned, so the task is not fixed. So given some goal configuration, the robot has to like do these kind of things to exactly match the positions of the cubes. And this one, I'm not sure whether you can see the humanoid here, but this is humanoid maze. So the task is to control this humanoid robot to reach some location in this like giant maze. And they're very complex and long horizon problems, up to 4,000 environment steps, but they're instant. So we can do control study. So anyway, that's like the description of the tasks. And what we did in these environments is that we collected almost like near infinite amount of data, such that overfitting is virtually impossible. In particular, we collected like place-style data set up to 1 billion transitions with 10 million atomic motions. As a comparison, like I think one of the largest robotic data sets to date, which is I think OpenX embodiment data set, which consists of like 2.4 million episodes. Even though it's not exactly apples to apples comparison, but like just in terms of their order, it's pretty much compatible. And it was possible because I'm doing like a sim here. Anyway, this is like how the data set looks like. So it's kind of random place type data set where the robot just performs random pick and place. Like sometimes it picks up some object and then places on top of other object, or sometimes it puts on some other random location and so on. And it does this like 10 million times. And then at test time, the agent is given some goal configuration. For example, here, the goal is like to stack 4 cubes like this. And then it has to perform this kind of 4 pick and place manipulation in this order to do this. And there are like 5. Yeah.
Can I ask how you define play style? So you manually define a policy, just doing random actions?
Basically, there's no like task segment, so it kind of continuously performs some random pick and place motions like this.
So heuristic policy that'll perform random motions with like random offsets to the blocks and things like that. Okay.
Yeah, exactly. Yeah.
Cool. Makes sense.
So the agent must be able to learn how to pick up some object and then place on top of other objects, or something like that. And another example, so this is puzzle where the data set is even simpler. Here, it's also place side data set. The data collecting policy is literally just random button pressing like scripted policy. So it really just literally presses button like 10 million times. So it's pretty kind of boring data set. But anyway, you can learn like how the dynamics work. At least that's like what the agent is supposed to learn, such that at test time, given some particular goal configuration, in this particular case, it's like turning everything in blue, and the agent has to press some combinations of buttons to match the goal state. So yeah, so these kind of tests are what we prepared for.
Oh, sorry. One last question. Sorry. Are these what's the reward for these? Are these both like, I assume they're like semi-sparse rewards, like one for every correct peg or something like that?
Yeah. Okay. So it's goal control. So the reward function is defined as the exact match between state and goal state. So it's like sparse reward, 0-1 sparse reward for all tasks that we consider.
Oh, so no semi-sparse, so fully.
No.
Okay.
It's like 0-1, only at the end. It's pretty challenging for that reason. But we have like a lot of data. So
even with your billion transitions, do you actually have any successes? I assume.
That's like what I'm gonna show.
Okay. Yeah.
That's kind of right.
All right, I'll let you go.
But anyway, before even like showing the results, I just also wanted to mention that in this experiment, we really tried to remove all confounding factors just to solely focus on like fundamental scaling of RL or like sequential decision-making capabilities. In particular, we focus on offline RL to abstract away exploration. I mean, exploration is important, but like it can also serve as a confounding factor, especially for online RL, because when it fails, we don't know whether it fails because of the lack of expression, or maybe it struggles to like fit a Q function or something like that. So I just wanted to like completely eliminate that concern by focusing on offline RL with sufficient amount of data. And we also did a lot of other things to ensure to ensure the environments are like as ideal as possible, like ensuring all the sufficient state coverage and data, and use state-based like observations. There are no pixel-based control, and also only use in-distribution tasks and so on. So here, the rationale here is that if the agent doesn't work, even in like these idealized environments with like almost near infinite data, then maybe there might not be like a lot of hope for RL to succeed in the real world, where we have limited data, we have noisy observations, we have to deal with like pixels and so on. So that's basically the rationale behind this design choice. But one thing that I wanted to make sure is that the data set is task agnostic. So it's like place style, unsupervised, like unlabeled demonstrations. It's kind of similar to the internet scale text image based pre-training or something like that. So I mean, we didn't specifically curate the data set for the test time task that we employ in the evaluation time. So yeah, that's the experimental setup. So this is kind of warm up. So what we did here is that we drew the scaling curves of behavior cloning and offline RL with different sizes of different sized data sets from 100K to 100 million transitions. First on easier tasks. So here it's cube double, so there are only 2 cubes. And here is the scaling curve. So the first one is flow behavior cloning, similar to like Pi0. And the other 3 are like pretty performant offline RL algorithms, like IQL, which is implicit Q learning, contrastive RL, and SAT plus BC. And then the x-axis is the dataset size from 100K to 100 million transitions, and the y-axis is the success rate. And you can see that they scale pretty well. Like for example, like 100 million data, just basically everything can solve this task almost perfectly, achieving 100% success rate, which is good. So it kind of checks the box that the dataset distribution is kind of good enough to enable this offline goal function like behavior.
So these easier tasks basically just have like shorter environment steps to get to the final reward, right? Is that how you define easier?
Could you repeat the question again?
So the way you define easier tasks, is it just like shorter horizon, like just very few steps to get to the final like reward?
Yeah. You're right. So
Okay.
here there are only 2 cubes, but like for the main task, we have like 8 cubes. So it's like cube octuple, but here's like cube double. So basically, the difference is that maybe the possible combinations of the like cube positions and also the horizon lengths. And on puzzle, it's like kind of small puzzle, so 4x4. And then here, flow BC doesn't work very well, even with 100 million. But this is kind of as expected. So the data set is collected by literally random button pressing pulses. So I think it's kind of natural that kind of BC struggles. But if you look at the performances of RL, they all, except like CRL, we can actually achieve almost 100% at the end with enough data. So this also kind of suggests that, for some simpler tasks, we can scale up things to master these tasks. The problem is that when the task difficulty becomes much harder, for example, puzzle 4x5. So here it's only one more column than this puzzle 4x4. But the thing here is that the number of possible states grows exponentially with respect to the number of buttons. So it's actually much harder than puzzle 4x4. And in this like harder environment, if you draw the same thing now with from 1 million to 1 billion transitions, things become pretty interesting. For example, if you do BC, it just completely fails. Maybe this is like still as expected because BC might not be able to solve these puzzles just by from like random trajectories. The problem is that even when we train RL, offline RL, they don't seem to scale very well. Like for example, regardless of the data set size, they often plateaus like around like 20%, which is like only 1 out of 5 tasks during evaluation time, and they show very poor scaling behavior in general. And the same for cube octuple. Here, unfortunately, none of them actually work at all, just across the board, regardless of the data set size, regardless of the algorithm. It seems like the results are pretty negative from this plot. Yeah, so I'm pretty sure that probably maybe the viewer or listener might ask whether I actually tune these methods carefully, or maybe they might ask, did I like, for example, try like even larger models, I don't know, for training for longer time, like longer epochs, or maybe did I try like more advanced techniques or something like that to somehow fix the scalability of RL? So to answer these kind of potential concerns or questions, we actually tried a bunch of quick fixes, whether we can actually fix the scalability of Q-learning by like tuning hyperparameters or adjusting some design choices. So for example, like we tried much larger networks up to I think 600 million parameters. By the way, that's actually pretty large given that the environment is like state-based. And I also tried like MLPs, res MLP, like transformers, basically better architectures and better pulses, including flow pulses and better regularization, larger ensembles, and so on, like many different hyperparameter tuning. The result is that none of them actually works across the board, regardless of the these advanced architectures or large networks. And in the paper, we actually put like this large evaluation study for sweeping over these kind of things. So and of course, it's really difficult to prove that it's impossible to scale up Q-learning because like that requires like trying all the possible like potential techniques, which I obviously couldn't do. But at least what's clear to me is that it's pretty difficult to scale up existing Q-learning algorithms with like standard-ish techniques. So that's kind of the point that I was making here. Yeah. So anyway, that's kind of the issue here. I am still maybe you can think about like this as a kind of my fault, but as an alternative hypothesis, what if it's not my fault? As an alternative hypothesis, it can be, what if actually Q-learning is false? For example, what if actually Q-learning is not as scalable in its current form, at least to complex and long pattern tasks? So I think this is also possible as an alternative hypothesis, and especially as I try more and more like techniques to fix Q-learning and then I fail, I kind of tend to believe like this statement. And also, especially considering like the anecdotal evidence that I mentioned in the beginning, like for example, like many of the real-world successes of RL are based on on-pulse RL for some reason. And also, in the literature, there are some works, some like really great works that try to scale up Q-learning, but they somehow mainly focus on scaling up Q-learning with more tasks and not necessarily harder or longer tasks. So basically, they train a single policy to like solve many different tasks at once. Like for example, for all Atari games. But the point there is that like they usually like there are not so many works that try to scale up Q-learning in the complexity axis. So to train a single policy to solve more harder tasks or more long horizon tasks. So the lack of such kind of method also somehow made me kind of believe this hypothesis, especially given the previous failure that I showed you. So yeah, that's basically the main hypothesis in the, at least in the blog post. Okay, so if this hypothesis is true, then we can also think about like, you know, what the problem is. Like why does Q-learning struggle to scale? Like what's the problem? Here's my answer. So this is also kind of hypothesis. I think Q-learning objective is actually very unique in the following sense. So in the Bellman objective here, the Q-learning objective has biases in the target here, meaning that this is not equal to Q star because it involves the bootstrapped previous Q value from like itself. And so that's actually bad. The targets are biased. But what's worse is that these biases accumulate over the horizon, right? So by minimizing the difference, temporal difference between adjacent two states, we are basically adding some bias to the Q function, and that like those biases actually accumulate over the entire horizon. So as the horizon becomes longer and longer, this issue becomes like more and more severe, and that's really bad. And actually, if you think about this, this is really unique to Q-learning. For example, if you think about other scalable objectives, such as like next token prediction, or like maybe diffusion, denoising diffusion, or flow machine, or contrastive learning, in these objectives, there are no biases in targets. And there, like we have some guarantee that if we have infinite amount of data, we can make the prediction arbitrarily accurate. But in Q-learning, it's very unique in the sense that the targets are biased. So my claim here is that maybe this bias accumulation might not be easily mitigated just by scaling up data and compute. And maybe that's why we are not seeing like very promising scaling behaviors with off-pulse RL or Q-learning. So that's kind of the hypothesis that I was making in the paper. And in the paper, we also did some like more controlled like study. So here, in some controlled environment, we actually measured like how bias accumulates over the horizon, and then as you can see in this plot, as the distance to the end becomes longer and larger, the bias just accumulates over time, meaning that this hypothesis might be like true, or at least like it's plausible. Yeah, that's kind of my hypothesis about the poor scalability of Q-learning. And of course, our goal is to fix it, right? So, I mean, we want to like run RL for robotics or many other problems. For that, we need off-pulse RL, and then we need a scalable off-pulse RL algorithm. So, we can think about like the solutions to fix Q-learning. And if we believe the previous hypothesis, if we believe that to be true, then maybe what we have to do to fix Q-learning is to reduce the horizon length, reduce the bias accumulation by somehow like shortening the horizon. There's many ways of doing this. Perhaps the simplest way of doing this might be to use some value horizon reduction via n-step returns. So basically, what we do here is that instead of training a single step like one-step TD learning, we train n-step TD learning. So basically, the Q-learning gets updates from like Q as h plus n instead of h plus 1, using like MC Monte Carlo returns during the n step. So by doing this, we can actually reduce the number of Bellman recursions by the factor of n. So that's like why I call it value horizon reduction.
So sorry. So this is saying you're skipping. So are you sending like a chunk of actions, or are you just actually skipping like 10 or n actions, right?
Yeah. So it's not action chunking. It's just skipping.
Yeah.
Yeah. It's kind of Monte Carlo n step returns. Yeah. So just to see how it actually potentially improves scalability, we also measure the same thing. So we trained n-step SAC plus VC, which is like one of the like great TD learning algorithms with the same sized data sets. And this is the previous result. So when I trained SAC plus VC, it didn't scale at all. Like it's kind of completely plateaus. But if you do n-step SAC plus VC, this was actually the first time I was able to solve this task, at least like to achieve non-trivial performance on this task, like beyond like 1 out of 5 task achieving at the evaluation time. So by reducing the value horizon, we can actually improve the scalability of RL. And also, this is the case in humanoid-based learning as well, as you can see from the difference between these two plots. So basically, my claim.
What is
Sorry?
the n that you use in this case? How many
Yeah,
steps?
so I think in this puzzle case, I used n equal 25. So it's like reducing the horizon by the factor of 25. And here, I think n is 50. It's pretty large. Yeah, it's like basically we can reduce the effective horizon to like a few hundreds or like around 100 or something like that. Even less than 100. And
Do you have a chart where you kind of like do a study with different n?
I think in the paper we didn't have some observations on n, but we really did need to tune this n pretty carefully. So for example, if n equal 1, then that recovers the original one-step TD.
Yeah.
That didn't work. But if n is like too large, then also it suffers from in this time like variance issue. So because the Monte Carlo estimate of the return can be very noisy. So in that case, also it doesn't work very well. So we unfortunately have to tune the value of n to somehow find the sweet spot in this bias variance trade-off.
Interesting. So
Yeah.
the n step does help, but you don't know before the fact what n to use.
Yeah.
And
so I think
you can
that,
only do it right now because you have the luxury of near infinite data.
That's kind of true. Yeah. And also I
But
have
still,
luxury to like evaluate things and then like tune the n based on the actual evaluation results.
got it.
But I would like to say that this is kind of, in some sense, inevitable in Q-learning. For example, without answer return, it's really difficult to scale up like Q-learning. That's I would like to say that it's like almost infeasible. I mean, of course, it might have used like exotic, like obscure techniques somehow that magically fix Q-learning, which I like just couldn't find. I don't know.
So okay, just because we mentioned this earlier, so you have this large n, and a large n is going to drive up the variance, which is going to make it harder to learn.
Yeah.
But the reason that it drives up the variance is because a lot of there's something unobserved, which is all the intermediate actions. So what would happen if you did action chunking here? Would that solve the problem?
Okay. I think eventually that can be the solution, and I think action chunking is somehow coincidentally also like one of the things that like especially these days many robotics folks like to use. And I think it also has like that like nice side effect. I mean, it's like a good side effect that it can potentially reduce the variance in the like TD learning objective at the expense of learning very potentially complicated Q function. So now we are kind of like putting all the burden
very difficult. Yeah.
Input Q function. So there's some trade-off there. So here, what I wanted to emphasize is that n-step TD learning actually improves scalability and moreover asymptotic performance by just reducing the value horizon. I mean, n-step return is actually not at all a new thing, right? I think it's also used in maybe one of the first like Atari DQN papers. But I mean, in many previous cases, people tend to think about n-step learning as a more like a simple trick to like accelerate training or like improve sample efficiency or something like that. But here my claim is that it's not just that. It actually improves asymptotic performance by reducing the value horizon. And also it kind of supports the previous claim that Q-learning, especially bias accumulation, somehow fundamentally inhibits the scalability of Q-learning. So that's like the point that I wanted to make here. So is it all we need? Can we now scale up Q-learning with n-step TD? It turned out that this is unfortunately not the case. For example, this is the like 8-cube manipulation task with like pretty hard like data set. Here, SAC plus BC like completely fails. And if you do n-step SAC plus BC with tuned n, it still like completely fails. So I was not able to make this work on like this task, even with like 1 billion data. So in the paper, we hypothesized that this is actually because, or in order to make Q-learning scalable, we not only need to reduce the value horizon by reducing the Bellman recurrence, but also we need to reduce the policy horizon. Basically, what this means is that we want to train a hierarchical policy so that each of the like hierarchical policies, like the high level and the low level policy, only kind of think about like like the square root of the horizon, like effective horizon, so that we can reduce the pulse horizon. And then we hypothesize that this can actually help improve the scalability of Q-learning or of pulse RL in general. And how can you do this? Well, to do this, we need to use some hierarchical RL. But probably, as you know, like many hierarchical RL methods are often pretty much like complicated because we need to train like two pulses, the high level and the low level pulse, and we also have to tune hyperparameters for each of the like two pulses, and then we also need to tune some RL like value learning hyperparameters. There are like so many things to tune. So in the paper we try to propose potentially one of the simplest like full hierarchical RL methods that don't require like a lot of tuning while reducing the pulse and value horizon so that we can improve scalability. So here's a recipe that we call SHARSA. The value learning objective is very simple. It's actually not even RL. It's just SARSA with n-step return. So basically, there's no like max over A or something like that. So it actually fits the behavioral Q function and value function with just like data set actions. And G means like goal because this is goal condition. For the policy, we have two pulses. One is high-level policy and the other one is low-level policy. And they are basically both trained with flow behavior cloning, or maybe you can think about this as like diffusion pulses. So basically, the high-level policy, given a goal, outputs a waypoint or a sub-goal, W, and then the low-level policy takes that W as input to output a row action. And these pulses are basically trained with flow behavior cloning, but I do additional reaction sampling only for the high-level policy. So basically, what this means is that I first sample n waypoints or subgoals from the behavioral high-level policy, and then evaluate the goodness of these waypoints based on the learned Q function from this like value learning objective, and then pick the argmax waypoint. So that's like the definition of the high-level policy. And the low-level policy is just literally BC. So basically, every component is trained with like either SARSA or flow BC. They are like in some sense like hyperparameter free, at least like RL hyperparameter free, which is good. And there's like one like bit for improving optimality, which is injection sampling. So I mean, the goal of this like method is maybe not to achieve the like best possible performance, but just to show that even with this simple technique, because we are reducing the horizons of the value and pulse learning, we can actually improve scalability at the end. So that's basically the rationale behind this method. So here's the result. So this is the test that I showed you, cube of tuple, and existing like cyclic BC or n-step cyclic BC almost like completely failed. But if we do SHARSA with both value and pulse horizon reductions, then actually we were able to achieve the first non-trivial performance on this task. Even though it kind of goes down with 1 billion data set, I think this is mainly due to the simplicity of the algorithm. But this is actually almost like the only method where we were able to achieve non-zero performance on this task. And in the paper, we have a pretty big plot about all the 4 tasks with a bunch of different horizon reduction techniques, including n-step plus VC or some other horizon reduction techniques, which I didn't explain here. But basically, the conclusion from this plot is that horizon reduction makes RL scalable. Hence the title of the paper. So yeah, that's basically my summary of the paper, and hopefully it makes sense to some degree.
Very cool.
Yeah, let me know if you have any questions.
Yeah, it's really interesting stuff. So
Yeah.
just off the right away, I guess it still seems like the issue is always exploration and how often these particular rare outcomes are even represented in the data set. So like one thing that strikes me, not just about the you had 3 examples of really successful reinforcement learning, right? They were AlphaGo, Dota, and 5, I guess is what they called it. Sorry, the third one was DeepSeek, right? All of those start with a really good base model that succeed like 70% of the time, right? Which does not look like it happened in this. So could you expand on that? Like, what do you think? Like, basically, is this now there are lots of domains where exploration is just not tractable. We don't have a base model, but like, how does that fit into what you're describing here? I guess.
So here it's more like kind of I try to abstract away expression in this paper. Basically, the argument is this: so even with the best possible base model, can we do RL in the real world for robotics? I mean, assuming that we have somehow
Well, we don't have
solved
the data to train a good base model. That's fair enough, though. Okay, yeah.
And my claim is that even with like the best possible like base model, I mean, unless it can just solve the task, to scale up RL, we really need to have some scalable off-pulse RL algorithm, which we may not have with existing technique. So of course, we also need to solve expression, which is a separate problem, like a very big topic, which I'm not like touching in this like paper.
Yeah.
But that's my basically stance.
Yeah, so Hong, I want to get your thoughts about just now you quoted Kyle saying basically on policy RL is a disaster for robotics.
Yeah.
So even just 100 steps is like 1-2 weeks of robotic time, right? So and you're saying that things like games and LLMs is things that you can simulate, let's say, pretty well, and you can do all the reset and therefore you can do it. What do you think of world models?
Oh yeah,
in some sense, they are data-driven simulation that you can reset very easily. Do you think it's possible?
I actually feel
do online, on policy RL just using world model and
that's actually a very good point.
Okay.
I think as a scalable solution to off-pulse RL, I do think model-based RL can be a very promising solution for the following reason. So what is model-based RL? This includes like word models that you mentioned. So we first learn a model, which is word model, using maybe like supervised learning. So this is actually supervised learning. We just predict the next state from current state and current action. We know that this is scalable because this is supervised learning. I mean, with infinite data, we can make this arbitrarily accurate, which is good. What we can do in this model is that we can actually run on-pulse RL purely within the model, like treating the model as a simulator. We also know that on-pulse RL is scalable. So by combining these two components, we are somehow combining two scalable components together. And maybe as a result, the resulting framework might also be scalable. And somehow, interestingly, the resulting framework can actually deal with off-pulse data. Because for model learning, we can actually use any like arbitrary like transition data. So I do think model-based RL is actually pretty promising for this reason, especially for the fact that we don't have to use like off-pulse Q learning. So yeah, I think it's a very promising direction. And actually, I'm currently also working on this just to see whether actually we can scale up model learning and like this on-pulse RL with the model with like near infinite amount of data. Yeah, that's my like one of the three potential guesses for like scalable off-pulse RL algorithm. Because just I'm just sharing the screen. Let me just also briefly explain the other two. So the first solution is, for example, we can somehow do recursive horizon reduction. So the problem with the existing horizon reduction, like methods like n-return and so on, is that they only reduce the horizon by a factor of n, right? And that's a constant.
It's fixed.
So yeah. So if the original problem length is like n times longer, then still we have to deal with the long horizon. So if there's some way to recursively break down the horizon, like for example, more like divide and conquer manner, so that we can limit the number of MR recursions by like log t or something like that, then actually we can deal with exponentially longer horizon, and that actually might be able to scale up to much longer horizon and much more complex problem. Another possibility is that maybe, I don't know, maybe some like exotic off-pulse RL algorithm might be actually might scale better than like more traditional Q learning. Like for example, there's one interesting method called quasi-metric RL, which actually kind of performs goal control RL based on some like interesting metric learning objective. And then it doesn't like depend. It's not based on like traditional like TD learning or bootstrap value learning. So maybe these kind of like, I don't know, very different things might eventually scale better than Q learning, which I don't know, but it might potentially be the case. And I do think finding a really scalable off-pulse RL algorithm is a very important problem even in just machine learning. I think we are having a lot of scalable objective for many other fields like NLP, CV, and even on-pulse RL. But I think maybe not only, but like in off-pulse RL, I think we are currently lacking a truly scalable algorithm. So I think we need more algorithmic research in this regard.
Yeah, so it seems to me the third one is like magic sauce that's to be
Yeah.
discovered. But the first one is like maybe slightly smarter way to deal with N. But the second one, I just want to tap on a bit more. So you consider something like a world model to be like a model base, and then you do on policy R within that model. What do you think will be the shortfall? Like, do you have some gut feel? I know you're exploring this activity now.
So
like,
are you asking like what do I think about the
yeah. like let's say you by the time we get to field 4, field 5, like basically you can't judge reality anymore. Like it is,
Yeah,
maybe humans can't.
I assume it would
Like
actually be a loop, right? Like you'd have to learn your model, train until convergence, test, and keep doing that.
yeah. I actually
Yeah.
do think
Yeah.
model-based RL can be I'm actually, how do I say, compared to like 4 months ago, I'm more avid model-based RL believer than before because of the potential pathologies with model-free Q-learning. I might change my mind after like spending more time in model-based RL, but that's my current belief.
Have you seen any results that have convinced you? Is it, or is it more just like you think the idea is the right one?
So we're actually currently working on this, and then we actually
Okay. All right.
train a word model, state-based word model in some puzzle environments, and then I was able to achieve pretty good performance, at least in puzzles, without horizon reduction. I think that's like due to the strength of like on-pulse seed. So I'm not sure like how it works on other environments. Like for example, actually in humanoid maze, we're currently struggling to make models work because the model has to fit very contact-rich dynamics, which seems to be pretty hard. But
Yeah.
still, like it's a supervised learning problem. So I think at least theoretically, we know that with like large enough model and with enough data, we can do that.
Yeah, so I mean, for that one, I mean, to get a damn good world model, you probably still need a lot of real world data. So I think,
Yeah.
So
But
let's say you want a
issue
very
is
good.
that, but we don't have to collect data in an on-pulse manner. So we can actually just collect data by just whatever means.
Mhm.
We can even use like YouTube video or something like that, and we can build very good word model and then do on-pulse RL within the model. This might be much better than, for example, actually doing like close loop on-pulse RL training with like human data collection. That's, I think, very hard to do.
Yeah.
There's probably some combination of the two that you could do because like I definitely feel like if things like contact dynamics are very local,
Mhm.
that's why they work so well with sim to real learning right now for locomotion.
Right.
But,
Yeah,
like,
yeah.
yeah. So if the world model is struggling with that, maybe it just doesn't need to deal with it. I don't know. You have the lower level in the hierarchy handle it. I don't know. That's really cool. It's exciting stuff.
Yeah.
Yeah.
Yeah, but I think anyways, like I said, I really enjoyed the blog post you wrote.
Oh, nice.
I think
Yeah.
rarely do we see a paper and then folled by another blog post to explain in further like layman term. But I thought that was a really systematic attempt to at least explain the problem and
I do like
and
it.
so
Yeah.
Yeah, I agree. I thought it was the paper they taught me and in the blog post because it's very. I think offline RL is something that seems so important to getting to really scaling robotics in general because like you're saying, on policy just doesn't work for most tasks, and yet, right?
But it sounds like
just
there's no
doesn't
hope
work
now.
as well. Yeah.
Now we're gonna pray for a
Right.
world model.
Yeah.
Or just
Right.
collect a ton of like the demo data and just either BC the hell out of it
Yeah.
or get a world model and then do online policy on it. But,
I think maybe
Yeah.
because like at least we have pretty good benchmark for testing, like at least like pushing the limit of the scalability of RL. Because we have these problems. Maybe hopefully I think maybe in a year or 2 years we might be able to actually find the like new or maybe scale up existing techniques like some solution to false RL. At least actually that's like one of my goals.
Feel about just using better reward functions though? I know it's like because one problem with the billion example, right, is that just like there's not going to be much signal, right? Because they're so hard to get there.
That's
But
actually
yeah.
very good way of doing horizon reduction. So basically, by using dense reward, we can actually can reduce the number of effective horizons, like the look-wise staff for the model. That might be actually very good practical solutions in practice. But as an algorithmic researcher, I want to find like more ideal like an algorithm that can actually deal with horizons of arbitrary lengths.
That makes sense. Yeah.
Yeah, I mean there are some works. I think what was the one that from Jason Ma was that the GVL. So it's giving you some kind of value function as you get along, that kind of thing. May not be super precise, but then it helps instead of 0 before you finally see a 1.
Yeah.
Right.
I think those kind of works can be somehow treated as Monte Carlo value learning. I mean, it's not exactly that, but somehow value learning without involving TD learning. And I think in that sense, it can be pretty promising because I think TD learning is kind of in my personal opinion, it's like the evil in the like all false RL. And I think we want to avoid it, especially when it comes to scalability. By the way, I have one thing that I want to mention before I mean this. There might be actually some like really like magical technique that enables scaling of Q-learning. For example, I mean, even for neural networks, Like I think it was developed like very long time ago, but it was only after like finding the right way to initialize network weights and use the right nonlinearity, then we were able to like somehow scale up like neural network training. And the same for like DQN. I mean, Q-learning, even in some toy environments, it didn't work, but like 2013, like I think the DQN authors found that using a target network or replay buffer actually enables working Q-learning on the target games. So maybe like these kind of very small tricks might actually somehow enable even the scaling of Q-learning. And maybe just we haven't found like that small trick. So I think I can also imagine that kind of feature as well, which is possible.
Yeah. Anyway, maybe as a wrap up, like we like to ask this question, like, is there any paper that you read recently you want to give a shout out to? Doesn't have to do with like, you know, all this like offline policy or whatnot. Like anything that that interests you, pique your interest. You want to give a shout out to?
Does it have to be like robotics paper or can
No, it doesn't have to be.
Anything.
Anything you want to just give a shout out to.
Okay, this is like too out of the topic, but I really enjoyed reading Gokul Swame's All Roads Lead to Likelihood paper. So it's actually about like RLHF and LLMs, but I really like the quality of the paper. So this is like one of the few like papers that actually stand out in terms of the quality. I can like feel like how much effort he put into this like work. So I still
What's it
remember
called
like,
again?
all roads lead to likelihood, or sorry,
Oh,
maybe I
think
missed.
yeah, I think reinforcement learning fine tuning, is it?
Yeah.
Goku. Oh yeah. Got it.
It's kind of related to RLHF, but I really enjoyed reading this one, and it's also excellently written.
Awesome.
It's like too out of topic paper.
Awesome. Yeah.
All right, awesome.
Yeah, thank you so much,
Thanks.
Seohong. I thought, at least I speak for myself, I learned a lot from that blog post you wrote. Yeah, so thanks for
It's
writing
very,
that.
very interesting, very thought-provoking work.
Yeah.
Great stuff. Thanks for going on.
Thanks again for like inviting me.